Video for our unit on applications of derivatives. So we spent unit 3 a long time, many weeks, talking about derivatives, how to find the derivatives, and differentiation rules, things like that. And so now we're going to kind of put it into practice. So this is just an extension or continuation of it. Lots more lessons, a lot of things to do, but you're going to see the actual applicable side of understanding what a derivative is. Okay, so this first problem, all right, is talking about a balloon, which is a sphere, is being filled with air at the constant rate of 2 cubic centimeters per second. We want to find out how fast is the radius increasing when the radius is 3 centimeters. So it kind of gives you a little figure here. And this idea of related rates comes from the fact that we're looking at two things happening here, right? The balloon is being filled with air. So as we do this, the radius is increasing, and we're going to really focus on the radius. But at the same time, as you can see in the little caption for the figure, is that the volume of the sphere is also increasing, right? The volume of the balloon is increasing as well. So that's two things that are changing with respect to time. So that's why this lesson is called related rates. So the first thing I'm going to do is I'm going to write down the formula for the volume of a sphere. All right, so we have volume equals 4/3 pi r cubed. Okay, and we want to find kind of what's happening here in terms of as the time is changing. So if we're looking at the change in one variable with respect to the change in time, that means we're going to find the derivative. So I'm going to find v prime of t as, and this is going to be using the chain rule. So 3 times 4/3 is going to be 4 pi times r of t squared. So r of t squared. And then times, right, the inside here, which is going to be the function for the radius, which is going to be, and we're going to find the derivative of that. So r prime of t. All right, so this right here is the kind of the first step, is to find the derivative of your function in terms of the volume of the sphere in relation to what's happening with the radius, okay? Now, once we have this, what I'm going to do is I'm actually going to move to the next slide because I have a few extra slides here for some extra work. But I'm going to rewrite this here on this next slide. So v prime of t equals 4 pi times r of t squared times r prime of t. I guess I should make sure you understand that that's my radius with time t squared. So essentially what I want to do here is using something in the beginning of the problem where it said that the balloon is being filled with air at a constant rate of 2 cubic centimeters per second, right? So this is affecting the volume, and the volume is being increased at a rate of 2 cubic centimeters per second. So what I'm going to do is I'm going to substitute where it says v prime of t, right? That's because that's the change in the volume with respect to time. I'm going to replace my 2 cubic centimeters per second right there because that is my change in my volume. Okay, now at this point, I am ultimately trying to figure out, if you go back to the original question, is how fast is the radius increasing when the radius is 3 centimeters? So essentially what I need to solve for is the change in the radius with respect to time. So I'm solving for this derivative of the radius. So I'm going to isolate for that by dividing both sides by 4 pi times r of t squared. So both sides. All right. So that's going to give me r prime of t is equal to 1 over 2 pi times r of t, all of that squared. Okay? Now again, at this point, I'm trying to figure out what happens when my radius is 3. So I'm going to plug in, right, if I'm trying to solve for this, I'm going to plug in 3 where I see my radius. So I'm going to do 1 over 2 pi times my radius, right? If it starts at 3 centimeters squared. So if I finish this, I guess I'll move to the other side since I have it. I'll move to the other side here. Do 1 over 2 pi times 9, which equals r prime of t. I'm going to find out that my radius is changing, right, with my units here of 1 over 18 pi centimeters per second. Okay, so for this next example problem, are going to be a little bit more complicated than what we just did. And I'm also going to go through kind of these steps right here to help us kind of understand how to do the problems. So the first one was just kind of getting the feel for it. But this one, I'm going to try to follow the steps. And the first one is to draw a figure. So we have an airplane. It's flying overhead at a constant elevation of 4,000 feet. There's a man viewing the plane from a position 3,000 feet from the base of a radio tower. The airplane is flying horizontally away from the man. If the plane is flying at a rate of 600 feet per second, at what rate is the distance between the man and the plane increasing when the plane passes over the radio tower? So I'm going to draw a little sketch here. So we have a man, then we have a tower. Let's see if I can fit it a little skinnier. There we go. Okay, now we have an airplane. I'm not even going to try to draw a plane. There's no way. So if you can draw a plane, good for you. Go for it. So I'm going to draw the distance here and the distance here. And essentially, we're going to be looking at when it's directly over that tower. Okay? Now, you can use whatever letters you want, right? It's up to you. But ultimately, you want to pick some letters because we are going to be looking at defining variables with relation to each other and with time. So it is important that we define them, all right? And essentially what I've decided to do is I'm going to use the letter X to denote the distance between the man and the distance on the ground right below the airplane. Now, I know it looks like that's the distance between the man and the tower, and I don't want you to think that's the case. The case is that it's the distance between the man and the spot directly below the airplane. We are eventually going to look at when that spot is the tower, right? That's the question. But in terms of defining X, it's not about the tower. And then the letter S is going to be the distance between the man and the airplane. All right, now remember the airplane is moving horizontally away from the man. All right, it tells us at a rate of 600 feet per second. All right, so essentially, if I look at the derivative of the distance between the man and the point below the airplane, right? Remember, we go from the position of it, then it's the velocity or the speed, all right? So the dx over dt is going to become 600 feet per second. We'll use that later on in the problem. Now, I'm also going to label the fact that we're looking for when the height of the plane is directly over a tower. We're going to be trying to find that the rate at which the distance is increasing between the man and the plane. So I'm going to label that as 4,000 feet because we know the height or the elevation of the plane is not changing. It's a constant elevation. So essentially, I'm going to be trying to find ds over dt. So I'm going to put that over here. ds over dt. So the rate at which the distance between the man and the plane is increasing when the airplane is directly over the tower. So that's what I'm trying to solve for. Okay, so now that we have kind of labeled everything, right, we're just a reminder, we're trying to find ds over dt when the distance between the man and the tower is exactly 3,000, or distance between the man and the spot underneath the plane is 3,000 feet, right? That's where the tower is. So the first thing I'm going to do is I'm going to write an equation that's essentially relating all these things together. So this is creating a right triangle, if you will, right? It does create a right triangle. So I'm going to use Pythagorean theorem to kind of write all this stuff related to each other. So we have x of t squared, right, all that squared, plus 4,000 squared equals s of t squared. All right, so that's using Pythagorean theorem. And then what I want to do is I want to differentiate this stuff, all right, because ultimately I'm going to use that to then solve for my unknown. You'll notice that my unknown, right, the thing I'm solving for, is ds over dt, which means I need to find derivatives. So I'm going to find the derivative of this equation that I just wrote. So it's going to be 2, you know what, actually I'm going to move to this slide over here. No, I'll stick with this one, that's fine. So 2 times x of t to the first power times dx over dt plus, now the derivative of a constant, right, 4,000 squared is just a constant, that's just going to be 0. And then this one's going to be 2 times s of t times ds over dt. All right, so you can see our unknown is in there. So I'm going to just kind of set these equal to each other real quick. So I'm going to have 2 times x of t dx over dt equals 2 times s of t times ds over dt. So the 2's are going to cross out. And so I'm just going to have x of t times dx over dt equals s of t times ds over dt. So this is kind of a checkpoint, if you will, when I'm trying to solve this issue. Now, at this point, if I try to solve for ds over dt, I'd have too many unknowns. I do know that we have x of t, right, that distance between the person and the spot directly under the plane is 3,000 feet. That's how far away the person is from the radio tower. And I know the speed, the rate at which the plane is flying with a 600 feet per second. But I'm trying to solve for the rate at which the distance between the man and the plane is increasing, which is ds over dt. But I don't know the distance between the man and the plane, that letter s. So what I'm going to do is I am going to take kind of a brief little moment and move to the side where I'm going to write down x squared plus 4,000 squared equals s squared. And I'm going to solve for s when x is 3,000. All right, so we have 3,000 squared plus 4,000 squared equals s squared. All right, and solving for s, if you need to go to decimals and do this, you can. I know from my days in geometry that there's a perfect right triangle called the 3, 4, 5 right triangle, as well as 6, 8, and 10. And so if this is 3,000 and then 4,000, then the hypotenuse, or letter s, must be 5,000. Okay, so now I have everything I need to kind of solve for my unknown. So I'll write that equation again. I've got x times dx over dt equals s times ds over dt. Okay, so I'm going to plug in the stuff that I know. I know we're looking for x is 3,000. The rate at which the plane is moving away is 600 feet. All right, that's the speed of the plane, equals 5,000 feet is the distance from the man to the plane. And now to solve for the rate at which the distance between the man and the plane is increasing. All right, doing some algebra here. All right, that's going to give me, let's see, 18 and then 5 zeros. Let's see, that's going to be 1.8 there. And then all over 5,000. All right, you can cross out some zeros if you'd like. I'm going to move to decimals to actually calculate what this number is. So if I take away 3 zeros, the 1,800 divided by 5. So 1,800 divided by 5. It's going to be 360. All right, I'll get my units. So this is 360, my units here, feet per second. So this is the rate at which the distance between the man and the plane is increasing when the plane is directly over the radio tower. All right. Okay, so this next example is actually from the beginning of the chapter. It's about a rocket that is launched vertically. We have a camera positioned 5,000 feet from the launch pad, and when the rocket is 1,000 feet above the launch pad, the velocity of it is 600 feet per second. We're going to find the rate of change of the camera's angle as a function of time so that it stays focused on the rocket. So again, I'm going to draw a picture. I have a camera here. It's on 5,000 feet from the launch pad. So here is the launch pad. All right, that's 5,000 feet. And our rocket blasting off. Here's the height of the rocket. And then you can see this creates a right triangle. Okay, now I've already labeled h for the height of the rocket as it rises vertically above the launch pad, but I'm also going to use another variable, and that variable is going to be theta, which is the angle between the camera and the launch pad. So we know that's going to change because it has to follow the rocket as it's blasting off into the sky. Okay, now the first thing I need to do is once I label these is I need to write some equation that's going to put these variables together. And what I notice is we have a right triangle. So I'm thinking about my trig functions from your basic geometry class. And what looks like, if you look at this theta, we have the opposite side, h, and the adjacent side of 5,000 feet. So if I think about SOHCAHTOA, I know you thought that was going away. It's back again. SOHCAHTOA for this would be tangent. Tangent is the opposite side over the adjacent side. So I'm going to write the tangent of theta equals h over 5,000. And I'm going to solve for h. All right, solving for h will move that 5,000 over a multiplication. So h equals 5,000 times the tangent of theta. Okay, so that's kind of my first step is to write that equation that relates both of these variables. Now the second step is to take the differential or find the differential equation with both of these with respect to time. So I'm going to find the derivative, all right, of this. I'm going to go to the next slide here and just copy this down. So h equals 5,000 times the tangent of theta, okay? And so taking this derivative with respect to time, you're going to have dh over dt, and this is just a constant multiple, so 5,000 times the derivative of tangent is secant squared theta, and then with the chain rule, we have the derivative of theta with respect to time. Okay, so that's kind of the next step is to find that derivative. Okay, now similar to the last problem, right? I'm not ready to plug in stuff yet because I have too many unknowns. Let me talk about the stuff that I do know, okay? So we essentially, according to this problem, are trying to find the necessary rate of change for this camera's angle, all right, when the rocket is 1,000 feet above the launch pad. So they're telling us, all right, they're telling us that the height that I care about is going to be 1,000 feet, okay? And they're also telling us that the rocket, all right, the velocity of it is 600 feet per second. So dh over dt is 600 feet per second. So again, I'm solving for, here's my unknown. My unknown that I want to solve for is the derivative of my angle, my theta, with respect to time. So that's what I'm solving for. But I'm not ready to solve just yet. I'm going to do a little kind of side step here. All right, you'll notice that I know what dh over dt is going to be, and I'm solving for the derivative of our angle d theta over dt. The thing that I need to kind of figure out with some trig is I need to figure out this secant squared theta. If I can sort that out, then I can plug in everything and kind of solve for the unknown. So what I want to do is go back to that original triangle. All right, and again, we're focused on the fact when the height is 1,000 feet above the launch pad. So I'm going to draw just another triangle. a smaller version of the one that I just did. Same triangle. All right, so this is 5,000. This is 1,000. Here's theta. Okay, and we're trying to find secant squared theta when we have an h of 1,000. So if I look at first the tangent of theta, right, the tangent of theta is opposite over adjacent. Okay. Okay, so actually I want to back up a little bit. I don't want to use that just yet. What I want to do first, before I get into more trig, is I want to think about the fact that I want to try to find secant squared. So if I just think about secant theta, all right, let's get the correct trig function here. If I want to think about secant theta, that's the same as 1 over cosine theta, right? Secant and cosine are reciprocals. All right, so I need to talk about first the cosine of theta. And when I use the cosine, think about SOHCAHTOA, that's going to be the adjacent side over the hypotenuse, right? So this right here is the hypotenuse. So I'm going to use my Pythagorean theorem to find what that length is. So I have 5,000 squared plus 1,000 squared equals the hypotenuse squared. Okay, so I'm going to go into Desmos to find out what that is. All right, so I'm going to do 5,000 squared plus 1,000 squared, right? And then I want to take the square root of that, right, of 26, 1, 2, 3, 4, 5, 6, right? So it's going to be 5,099.01951351359. So I'm just going to write the rounded right now, but when I come back to do this, I'm going to use the one that's not rounded. So I'm just going to round it right now to 5,099. So that is our hypotenuse. All right, I'm trying to find secant squared. So I need to find 1 over the cosine of theta. All right, now I need to square it. Okay, so if cosine is the adjacent over the hypotenuse, then secant is going to be the hypotenuse over the adjacent side. So I'm going to write down secant squared theta is going to be like I said, cosine was adjacent over hypotenuse, so it's going to be hypotenuse, so 5,099. Let's put that all in a big parentheses. Remember, I know I'm rounding it. Over the adjacent side of 5,000, and all of that squared. So I'm going to do that again, go to Desmos, and take my 5,099 number, divide it by 1,000, and then square it. That's going to give me the secant squared of theta. So I'm going to take this number, right, put it in the numerator, and then in the denominator put 5,000, and then I want to square this. Which gives me 1.04. So that whole thing, right, secant squared theta, which I need, is going to be 1.04. Okay, so now I'll highlight this to help my brain. If it helps you, great. If it doesn't, I'm sorry. So now I have everything that I need to find my unknown, which is d theta over dt. All right, so I'm going to copy down that formula again, which was dh over dt equals 5,000. Okay, now I'm going to plug in secant squared theta since I know it, which was 1.04 times d theta over dt. And I'm going to go ahead and plug in my dh over dt now that I know it, or now that I'm ready to solve, which is 600. So essentially I just copied down the formula from before, plugged in the stuff that I know, and using my calculator, Desmos, I can solve for d theta over dt. So 5,000 times 1.04 and do 600 divided by that. So I'll move this to the side. So we have 600 over 5,000 times 1.04. Oop, that's not it. There we go. All right, so 0. It says we can do the fraction. Oh, nice. So either way, you can do the fraction or the decimal, 0.115 or 3/26. I'm going to use 326. Okay, and then to get my units here, right, we're talking about this angle that's changing. All right, it doesn't say what units we're using for the angle, so you guys learned in trigonometry that if it doesn't use any units, you should assume radians. So this is going to be 326 radians per second. All right, so that is our answer for the question about the rocket. Okay, so this last example here is talking about that water is draining from the bottom of a cone-shaped funnel at the rate of 0.03 cubic feet per second. All right, they give us the height of the funnel, which is 2 feet, and the radius at the top is a foot. At what rate is the height of the water in the funnel changing when the height of the water is half of a foot? All right, so I'm going to draw a sketch here. I'm just going to draw a triangle for my funnel. All right, so this is supposed to be a cone. All right, we have the water coming out. All right, and we have the radius, or I should say, let's start here. The height of the funnel, which is 2 feet. And then we have the radius, which is, this is the height. The radius is 1 foot. And then I'm not sure where the water is, but I'll just draw, it's just a sketch, and I'll color it in with some blue. Let's see, there we go, not too bad. So essentially, here's my water in the cone. All right, and we're trying to figure out at what rate is the height of the water in the funnel changing when the height of the water is half a foot. So I can make, this is the height of the water, which is half a foot. So height equals 1/2 a foot. All right, and then I'm not sure what this new radius is going to be. Okay, so what I'm going to do first is I'm going to write down one of our formulas that's going to kind of relate all these things together. And the first thing I'm going to do is I'm going to look at the fact that it's mentioning that the water is draining out at a rate of 0.03 cubic feet per second. I noticed that cube on the foot, and it makes me think about the volume. So I'm going to find the volume of a cone, which is 1/3 pi r squared h. All right, and if you don't know that, obviously it's no problem. Just make sure you Google it. Excuse me. Oh, excuse me. All right, so I'm going to continue on the next slide with that idea that I'm using. The volume of a cone is 1/3 pi r squared h. Now, there's too many variables going on here. I have 3 of them. In terms of what I know that the rate at which the water is escaping or draining out of the cone is negative 0.03 cubic feet per second. So that's my dV over dt. And we're trying to find the rate at which the height of the water is changing. All right. So I'm trying to find dH over dt, right? That's my question mark. So I'm going to look for a way to mathematically get rid of that letter R. And what I'm going to do is I'm going to see in this drawing, which I'll just leave this as H for now, all right, that we actually have similar triangles. And you guys learned in geometry that if you have similar triangles, you can set up a proportion to help you solve for anything you might need. So if I have R over H, right? So I'll make sure you're not confused by my letter R's. R is in terms of the water, the radius of the height of the water is at a certain spot, and the H is the height of the water. We know that's always going to be equal to the fraction 1/2. So if I do that, all right, and change R to be by itself and move the h over, that's going to be the same as h over 2. So if I use this new understanding and replace r in my equation, I'll have 1/3 times h over 2 squared times h. Keep doing the algebra. I get 1/3 pi, and that's going to be h squared over 4 times h. So clean this up, and you get, let's see, I'll get pi, I'll keep it as a fraction here, so 1/12 pi times h cubed. Okay? Now, I'm going to take the derivative. So dv over dt equals, right, 3 needs to multiply by 1/12, which is going to be 3/12, which is the same as 1/4, right, times pi, that's just a constant, all right, and then times h squared times dh over dt. Now I'm trying to find dh over dt when the height of the water is at 1/2 foot, right? It says the height of the water is 1/2 foot. So I'm going to plug in what I know, including that h is 1/2. All right, I'll do it. I'll finish it in my last slide here. So I have dv over dt equals 1/4 times pi times h squared times dh over dt. So I'm going to plug in my negative 0.03 equals 1/4 times pi times my height is 1/2, so squared times dh over dt. So this is now an algebra problem, just solving for my unknown. I'm going to clean it up a little bit before I go to Desmos. So that's going to be 1/2 squared, which is 1/4. So that's going to be 1/16 times pi times dh over dt. So now I'm going to move to my calculator to solve for that, the rate at which the height of the water is changing. So I'm going to multiply negative 0.03 times 16 and then divide it by pi. So let's delete all this. We have negative 0.03 times 16, and then take that negative 0.48 divided by pi. All right, so our answer is going to be negative 0.153. Negative 0.153 is going to be dh dt, and that's going to be feet per second. All right, so that is the rate at which the height of the water is changing when the height of the water is 1/2 foot. All right, so hopefully you'll have a chance to practice some of this and go over it. I understand this is getting pretty complicated right away. There's a lot going on. We'll practice a lot and make sure you feel confident before the test in many, many, many weeks. Good luck.